Modern artificial intelligence relies on massive scale. We are now seeing models with trillions of parameters powering highly complex, real-time agentic systems. But you can't build the machines required to run these models simply by buying thousands of powerful GPUs and sticking them all in the same room. If you plug 1,000 advanced chips together without a highly specialized communication network, they will almost immediately choke on their own operations. Raw computing power means very little if the data those processors need to crunch can't physically move between them fast enough. For years, the standard way to connect computer components has been the PCIe bus. Engineers originally designed PCIe to handle basic peripheral devices like graphics cards and storage drives. Think of it as a single, highly regulated hallway connecting different rooms. When GPUs train a large language model, they constantly share massive blocks of memory. Traditionally, all that dense information has to squeeze entirely through one narrow central pathway. Because everything is routed through limited lanes, multi-million-dollar GPUs are forced to sit completely idle. To scale up computing and build true AI factories, system architects realized they had to completely abandon traditional motherboard design. NVIDIA engineered a completely different path called NVLink. They bypassed the narrow PCIe bus for high-speed point-to-point links between processors. These private highways allow one GPU to reach right into another's memory pool without asking the CPU. Instead of taking turns, millions of parameters synchronize instantly across the grid. A congested multi-GPU setup suddenly begins to operate as a single, highly efficient computational pool. This chart tracks bandwidth escalation. Starting with Pascal at 160 gigabytes per second, it climbs to Hopper at 900, then capacity leaps. Blackwell hits 1.8 terabytes, and the upcoming Rubin architecture pushes to an enormous 3.6 terabytes per second. At 3.6 terabytes, Rubin will process data at more than 14 times the speed of a comparable top-tier PCIe connection. But to manage speeds that extreme across dozens of chips simultaneously, the connections require a physical traffic director, a companion hardware called the NVS switch. By pairing fast individual links with high-capacity switches, hardware engineers turned a simple hardware cable into a sprawling multi-device mesh network. During the recent Blackwell platform announcement, NVIDIA heavily emphasized this fifth-generation networking fabric. It's the core system that allows their GB200 server rack to link 72 individual GPUs together with massive all-to-all bandwidth. The hardware configuration effectively erases the physical boundaries between the chips. An entire liquid-cooled cabinet can now function as one giant super GPU. Without this level of rack-scale cohesion, building the infrastructure required for complex, real-time agentic AI would be physically and economically impossible. The foundation for this scale was proven in massive supercomputers like Sierra, where high-speed cohesive memory access first demonstrated how effectively distinct nodes could tackle heavy computations together. Architecture is iterating faster than ever. To track what systems launch next, join r/AI programming hardware on Reddit. The ceiling for artificial intelligence is no longer dictated entirely by a processor's raw speed. It depends on the invisible highways engineered between them.